Hello, everyone, and welcome to the webinar. Our topic today is shear wall selection for wood frame buildings. My name is Karen Beatty. I'm the Western Region Manager for APA Field Services Division, and I'll serve as the moderator for today's session. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood products and the systems where they are used. We also educate users and specifiers on the product's intended use and potential applications. Before we start our webinar, I'll go over some housekeeping details. And while we're bookending our discussion with our cameras on, we will be turning them off during the session to maximize the slide size on your screen. Our class today is approved for both AIA and ICC continuing education credits, and a certificate will be provided to use for AIA, ICC, or other organizations that self-report continuing education. Your feedback is important to us. I'd like to point out that you see a QR code on your screen. To open the code, you'll take your smartphone, point it at the screen on the link, and it'll take you to the survey for this session. We'll show this link to you a few more times throughout the course today. Our presenter today is Ron Nuttall, an engineered wood specialist for the Field Services Division of APA. Ron is a graduate from Texas Tech University with a degree in business administration and joined APA in 2017. He began his career with Georgia Pacific's distribution division in Texas and relocated with GP to their Denver sales center in 1996. After leaving GP, he promoted engineered wood products for both truss joists and Blue Links before joining APA. His responsibilities for APA include consulting with builders, designers, and code officials in the North Central U.S. Ron conducts CEU-approved workshops for designers, code officials, and other building professionals on the best practices for specification, selection, and application of engineered wood. I'll now turn the microphone over to our speaker, Ron Nuttall.
Thank you, Karen, and to everyone participating in this webinar. So let's get started. On the screen, you're going to see a copy of the course description you were provided upon registration. We want to help you understand the structural implications of your design to help in collaboration between architect, engineer, and builder. Here's a list of the learning objectives that we'll cover during this session. We'll identify the IBC shear wall options. We'll identify the differences between the IRC and IBC lateral resistant requirements. We're going to discuss the impact of architectural designs on shear wall solutions, and we're going to describe the resources from our website on the topics covered today. So what is a shear wall? We're going to talk about what a shear wall is and the differences between the braced wall panels and versus shear walls. How shear wall options are determined by the type of building you're designing and what is allowed in the IBC and IRC. Comparison of shear wall options in regard to what you're trying to achieve architecturally, which is and what is best structurally for your project, and how those decisions affect the constructability of the project. And we will provide those APA resources for both wall bracing and shear walls. What is a shear wall? They're walls that are specifically designed to resist lateral loads. An engineer calculates the lateral loads the wall carries to determine the panel thickness, nail size, nail spacing, and other detailing. This design will often include additional hardware. Here you can see a number of clips and steel straps. This wall also includes hold downs at each end on the ground floor. The term shear wall only applies to the specific portion of the wall that is resisting lateral loads. Just because there is sheathing does not mean it is a shear wall. When an engineer designs a structure, they look at all the loads that are applied to that structure and then create what we call a load path for each of those loads. There are two kinds of load paths, vertical and lateral. Both need to be complete for a structure to be properly designed. They're both required in the IBC and IRC. And the purpose of the load path is to take the load from where it is applied to the structure get it down into the foundation and into the ground. Every load that is applied to the structure must have a load path that takes it to the foundation so that it can exit the structure. Everyone understands the vertical load path. It's just gravity, and we're all familiar with gravity. The vertical load path takes loads like snow loads on the roof, the weight of the furniture and people in the house, and the weight of the house itself, also known as dead load, from where they are applied to the structure down to the foundation. The lateral load category consists of wind loads and seismic loads. The lateral load path is not as intuitive. One of the things people find surprising about lateral loads is that in some cases, these loads actually move upward through the house before they move back down. But just like vertical loads, all lateral loads must have a path that ultimately takes them down to the foundation and out of the house. Let's take a quick look at how walls resist loads. A stud wall by itself without any bracing, such as wood structural panel, has very little stiffness. When a load is applied to a wall that doesn't have any bracing, the nail joints between the studs and top and bottom plates act like hinges and are actually called hinge connections because they bend easily. The wall can be pushed over by a load applied at one end with minimal effort. When a panel type product is attached to wall framing, the panel's ability to resist forces is imparted to the wall. This is why panels are commonly used as the lateral force resisting system. They resist being forced out of shape. The ability of a panel to resist loads is dependent on the physical properties of the panel, primarily its thickness. The thicker, more rigid each one of those panels and more panels that are added to the wall line, the more resistance or strength the wall gains. Fasteners used to attach the panel to the framing will also affect the lateral resistance of the wall. Tighter fastener spacing and larger fastener size will increase the strength of the wall. The sheathing makes the hinged connections rigid connections and transfers the lateral load through the panel to the bottom of the wall. In other words, the panel becomes part of the lateral load path. There are three types of lateral load failures: racking, base shear, and overturning. Now, sheathing might provide the resistance, but if we're not getting that load into the sheathing, it can't help. This is why the attachment of the sheathing gets special attention. The sheathing nailing and thickness are two easy ways the engineer might be manipulating the stiffness of the wall. If you don't get the nailing that matches the drawing, it will affect load distribution. The damage shown in this picture is a good example of racking. The wall sheathing on the front of the home was incomplete at the time of the earthquake, so you can see the parallelogram shape of the house. Anchor bolts are specifically intended to prevent sliding failure. They're typically designed for horizontal loading only. This house remained relatively intact, but it slid 45 feet off of its foundation during a tornado. The overturning loads exerted on the anchors are higher at the end of the walls. That's why we see a heftier hold-down anchor or tie-down rod at the shear wall ends. These hold-down anchors typically have a deeper embedment at the bottom and more robust connection to the wall framing. Let's take a closer look at how overturning happens. If we have a wall with only one panel as a wall bracing, when the load is applied at the top of the wall as shown, the wall will want to tip over, with the bottom or left side of the wall tilting away from the ground. This is similar to what happens when you try to push a tall, skinny filing cabinet. It wants to tip over. This is what can lead to overturning of a structure and is why hold-down straps are required in some situations. They prevent the wall from tipping over and literally holds the house down. By adding more panels to the same wall, you will reduce the overturning load and reduce or eliminate the chance of overturning the structure. It would be like taking that tall, skinny filing cabinet and adding more cabinets or stretching it out. Now, when you try to push on it, it's less likely to overturn. This is why engineered houses have limited locations for bracing, typically need hold downs, and prescriptively braced houses typically don't, except for some methods that use narrow braced wall panels. The prescriptive bracing section of the IRC, section R60210, makes sure to require enough linear footage of braced wall panels to prevent the overturning. thus eliminating the need for hold downs in most of the methods allowed by the code. Hold downs must be installed properly to be effective. One error that is commonly observed is improperly locating the hold downs. When the wind blows from the left, the lower left corner of the panel will experience the largest overturning load. So this is where the hold downs need to be located. When the wind blows from the right, the opposite is true. In this photo, both hold downs are installed on the right side of the panel. When the wind blows from the right, the panels will probably be okay. But when the wind blows from the left, there's nothing to provide a load path for the overturning load that will occur on the lower left corner. Without a complete load path, the panel is likely to separate from the foundation. Hold downs should be installed on the furthest edges of the panel to be the most effective. Putting it all together, the shear wall components are sheathing, which is used to transfer the in-plane force. Blocking is used to stiffen the wall and increase shear capacity. And cords are at each end of the wall, which are composed of hold downs resisting tension forces when needed, and the studs at the end of the walls resisting compression. Shear walls are limited to an aspect ratio of 3.5 to 1. A higher aspect ratio typically means the higher wall deflection when pushed to capacity. Remember, deflection and stiffness go hand in hand, so this will also matter to our force distribution. I'll discuss aspect ratios a little later. With a better understanding of what a shear wall is, now we're going to look at what may be the best option for your structure. The options depend on what type of building you're designing and what the IRC or IBC allows. For single-family structures, you can use the IRC, the IBC, or a combination of both. The evolution of home designs went from simple box designs of the past to complicated homes of today. Prescriptive solutions using IRC wall bracing are fairly straightforward. Just follow the recipe. However, the code has changed over time and that recipe has become quite long. Engineered solutions using IBC shear walls allow more design flexibility, but require engineering review. A hybrid approach using both can be the best of both worlds, but you have to make sure the two solutions are clearly differentiated on your plans. Homes in the 50s and 60s were fairly easy to design for lateral loads as they were rectangular with small openings, usually single story, and had single car garages. In the 70s to the 90s, we started seeing larger homes with larger openings, offset exterior walls, and two-car garages. Today's designs are far more complicated with window walls, grand entryways, and irregular shapes. The ICC and APA jointly publishes a guide to wall bracing for each edition of the IRC. The last version is the companion to the 2018 IRC. The 2021 edition should be available shortly. Like I said, to determine the wall bracing per the IRC, just follow the recipe. Determine the seismic design and wind speed categories. Check for any disqualifying characteristics, such as irregularity requirements for seismic or heavy snow loads for wind. Check the number of stories, wall heights, and spacing between wall lines. Then you select your bracing method, intermittent or continuous, and your bracing material, wood structural panels or gypsum board, etc. Lay out the bracing panels per IRC requirements for placements and length of BWPs, and then confirm the braced wall panel's resistance is greater than the lateral loads, and you're done. What differentiates shear walls and braced wall panels? Both resist lateral loads. BWPs can look just like shear walls. Both may contain hold downs or strapping to transfer the loads. BWPs are prescriptively designed per the IRC. BWPs, except for the narrower methods, use only standard nailing patterns of 6 inches on the perimeter, 12 inches in the field. Instead of a minimum panel width, shear walls have aspect ratio limitations, the ratio of the height versus the width. But when do you use a shear wall instead of a braced wall panel? If your building does not fit within the limitations of the IRC, for example, the building isn't residential or it's over 3 stories, or the layout just precludes it. If there's not enough solid wall area to meet the prescriptive requirement, the designer will also turn to an engineered or partially engineered solution. For many engineers, they may have had very limited or no exposure to the residential code. In this case, they're going to often default to their more familiar option. The IRC lists 9 different building materials and 7 different methods that can be used as BWPs. But what about materials that aren't listed in the IRC and IBC? It is our position that the local code authority has jurisdiction to approve building materials and methods not specifically prescribed in the code. When major wind or seismic events happen, APA will often go out and survey the damage. In 2017, APA documented this down in Texas, where the wind speed was only estimated at 100 to 110 miles per hour, and the design wind speed was 115 miles per hour. After documenting the damage, APA and 2 universities did some testing, and a summary is available in a product advisory on the APA website. I've blown up a chart depicting the percentage of published capacities that each round of testing achieved. So this is 100% of the published value. The product advisory also includes a discussion on ductility, but it's important to understand, as new materials hit the market, what kind of performance indicators we need to be looking at before assuming they're equal. The 2021 special design provisions for wind and seismic, or SPIDWIZ for short, which is how we'll be referring to it later on, now directly references the ASTM D7989 standard used for this testing. Whenever looking at an alternative sheathing product, ideally we're getting better at predicting these performance deficiencies before something like this happens, but every failure is a learning experience. The first step in shear wall design starts with determining the loads that need to be resisted. Chapter 16 of the IBC governs the structural design of buildings and refers the designer to ASCE 7 for additional guidance. Earlier, we viewed examples of how single-family structures have evolved. Here are some examples of how commercial structures have evolved. This Church of Christ was built in the 70s, as was this apartment building. Back then, unattached garages were a luxury. Most apartment buildings only had parking spaces, very basic designs. The Cathedral of Christ the Light was constructed in the early 2000s and is highlighted in one of our case studies available from our website. On the right, apartments are increasingly built as 3/1 or 4/2 podiums with parking garages and/or retail space and office spaces on the bottom levels. When an engineer goes to design a wood shear wall, the primary reference is the special design provisions for wind and seismic, or SPIDWIZ. This book is published in conjunction with the NDS, which means the National Design Specification, by the American Wood Council. In this book, there are 3 methods listed for designing a shear wall: segmented, perforated, and force transfer shear walls, which I'll refer by the acronym of FTAO. What about CLT? APA represents a number of mass timber manufacturers, and this is a hot topic right now as jurisdictions across the country start adopting the tall mass timber provisions. The 2021 IBC allows up to 18-story tall wood buildings. The 2021 SPIDWIZ now provides guidance on CLT diaphragm and shear wall designs. AWC and Woodworks both have a number of educational resources to help you navigate designing with this new material. As a special note, CLT is going to use a different response modification coefficient than the 6.5 used in light frame wood shear walls. This is because the behavior during a wind or seismic event is not the same. Today, we're going to focus on light frame construction only, not mass timber. For wood structural panels, the shear values in SPIDWIZ are a function of fastener size and spacing, panel thickness, and the specific gravity of the framing material. SPIDWIZ Table 4.3a provides nominal unit shear capacities for wood frame shear walls using wood-based panels. Contrary to IRC wall bracing, there is no recipe for shear wall design. The engineer will analyze the loads and then select the shear wall design approach. It is important to note that you don't have to use one design method throughout. For example, segmented and FTAO can be mixed throughout the structure, even within the wall line, provided the engineer provides adequate load transfer detailing. Here's a side-by-side comparison of the three shear wall methods. Segmented, which is the traditional design approach, uses individual full height wall segments, but does not allow openings. The next two options, perforated and FTAO, do allow openings within the shear wall. Both allow the utilization of the full wall geometry, including the sheathed areas above and below openings. Perforated shear walls is an empirical design method based on the percentage of full height wall segments adjacent to openings. And force transfer walls, FTAO, is rooted in structural analysis. Historically, there was minimal testing of this method until APA's research, which we'll discuss further. But now let's take a closer look at each of these approaches one at a time. For segmented wood shear walls, only full height wall segments are considered, and the contribution of the wall sheathing above and below openings is ignored. The total height of the wall is used to determine the pier aspect ratio, or height to width ratio. For example, an 8-foot wall with a 4-foot panel has a ratio of 2:1, and hold downs are typically needed at each end of each shear wall segment to resist overturning forces. Similar to the segmented shear walls, the height and width ratio for perforated shear wall piers is again dependent on the ratio of the total height of the wall over the width of the pier. Unlike the segmented shear walls, perforated walls are accounting for the sheathing above and below the opening, but the openings have some restrictions. Steel anchors at the base of full height piers are required to resist both uplift and shear, but hold downs and anchors are only required at each end of the total wall length. Here's the adjustment table used for the perforated method. The designer will determine the shear capacity factor based on the geometry of the wall, the percent of full height sheathing and openings. The factor reduces the shear wall capacity and increases the design value for the hardware. This makes sense if you consider that as your wall has more openings, you have less capacity in your wall and would have a greater need for hardware to compensate for that reduced sheathing. FTAO has some rules for using it, but SPIDWiz doesn't give specific direction for the analysis, which we'll come back to in a moment. Just like perforated shear walls, we're accounting for the sheathing above and below the opening, and we're only placing hold downs at the very end of the wall. Here we're using straps to reinforce the corner of our opening and transfer that lateral force down to the base. One major advantage of FTAO shear walls is that the height to width aspect ratio is dependent on the height of the opening adjacent to the pier, allowing for reduced pier widths to meet the aspect ratio requirements. APA led a joint research project to examine forces generated in these wood-framed FTAO shear walls during a wind or seismic event. This research is the basis of our FTAO design approach and calculator. The study was initiated to evaluate the effects of size of openings, size of full height piers, different aspect ratios, and different construction techniques. We also wanted to measure the internal forces generated and compare to different FTAO analysis methods. And finally, we wanted to create a calculator to assist designers with designing wood frame structures using the FTAO method. We surveyed design offices and found that there are 4 techniques that are most commonly used to predict force transfer around openings: the drag strut analogy, cantilever beam analogy, the Diekman method, and the Thompson method. This slide summarizes the calculated strap forces on an example shear wall using each of the 4 analysis methods. We find that the drag strut analogy yields a maximum corner force of 489 pounds. The cantilever beam technique results in a corner force of 2,779 pounds. And the Diekman and Thompson methods result in maximum corner forces of 979 pounds. A more detailed explanation of these techniques in this example are covered in APA's webinar, Advancements in Force Transfer Around Openings, that can be viewed at apawood.org. So this is a pretty wide range of results. It was one of the focuses during the research project. What is the most accurate analysis method for FTAO? There were 12 total configurations tested. So let's go through a handful of them so you understand the variables APA was looking at. It's important to note here that the total wall length and height remained constant. All the nailing remained the same, and the same type of sheathing was used on all test specimens. Beginning with wall 1, you can see we have a 3.5 to 1 aspect ratio for our wall piers, with 2 foot 3 inch pier lengths on either side. Sheathing was only located on the full height segments with hold downs at either end, so we're recreating a segmented shear wall with wall 1. Wall 2 is similar to wall 1, except now we have sheathing provided above and below the openings as you would have in a perforated shear wall. No strapping or blocking around the opening was provided for wall 2, and 2 of the hold downs that are in wall 1 have been eliminated. Wall 4 was our first wall that had the full FTAO detailing. Wall 4 has the same geometry as wall number 1 and 2, with sheathing above and below the openings, and only 1 hold down at the left end and 1 at the right end of the wall. We also have the strapping provided on the exterior of the wall. Wall 5 has a similar detailing to wall 4 with the corner straps and blocking, except now the opening size has increased with a smaller area of sheathing below the opening. Wall number 12 was our last FTAO configuration and provides us with some great information for going around multiple openings with asymmetric piers. We have different pier lengths for each full height wall segment with hold downs at each end of the wall and strapping located at the corners of both openings. This wall was the focus of our testing and subsequent FTAO resources, since these types of wall configurations hadn't really been studied before. Looking at wall 4 configuration, which again is the FTAO method, we have relatively narrower pier widths with a deep sill. Comparing the effects of a bigger opening size in wall 5, which again is the FTAO method, we saw decreased stiffness and larger corner forces than in wall 4. But both walls are stiffer and stronger than the segmented and perforated walls. Now let's look at the results of the strap forces that were measured during testing. This chart is a comparison of the measured strap forces and the predicted strap forces per the 4 design methodologies. When you're looking at this chart, look at the areas highlighted in yellow and green. You can see each of the wall configurations we tested identified on the left. The yellow color coding represents cases where the forces calculated by the analysis methods were less than the forces measured in the lab. The green color coding represents the cases where the forces calculated by the methods were greater than the force measured in the lab by at least 300%. So we can see that the drag strut technique results are unconservative for most of our wall configurations. On the other hand, we can see that the cantilever beam method is primarily green, particularly on the top force or the force above the opening when we compare our analysis results to what was measured. That leaves us with Dinkman and Thompson techniques. These methods really are the most accurate when compared with the wall configurations that we tested. Looking at wall 12 once again, this configuration has the full FTAO detailing with multiple openings and asymmetric pier widths. Laboratory testing determined that the Dinkman method was the most accurate analysis method to estimate the forces in the shear wall. So we chose to use the Dinkman method as a base to expand the methodology to incorporate multiple openings and asymmetric piers. We use this for the basis of our FTAO calculator, which we're going to cover later in the training. So now let's compare the shear wall options structurally, architecturally, and their constructability. Let's take a quick look at the structural design comparisons. In the segmented method, the pros is that it's easy to design. The cons are that there's limited wall areas to work with. It requires additional hardware, and it doesn't take into account the capacity of the sheathing above and below openings that are outside of the designed designated shear wall segment. It can be hard to meet the aspect ratios of this design method. For the perforated method, the pros are that it's relatively easy to design. You get to use the capacity of wall sheathing above and below openings, and it reduces hold downs. The cons are that designers have to use the full wall height for the aspect ratio. They have to design for uplift at each full height segment. And some engineers don't like the limitations of the adjustment table that we showed earlier. The pros for FTAO are that it allows the most design flexibility with regard to aspect ratio. Remember, we get the narrowest shear walls. It accounts for the sheathing capacity above and below windows, and there are fewer hold downs required. The cons are that it is the most complicated design method, but we do have a free calculator to use, which we will be going over in a little bit. And it may, but not necessarily, require strapping at opening corners. Here's the design summary as detailed in our shear exhilaration webinar, which is found on our website at apawood.org, and it compares the three design methods. You'll notice the same sheathing was allowed, but the nailing was slightly tighter for the perforated and FTAO compared to the segmented approach. But both perforated and FTAO have fewer hold downs, which can be challenging to install. The FTAO approach does have additional strapping compared to the perforated approach, but the hold downs are smaller. As stated at the beginning, generally the driving factor for FTAO is where you don't have a wall long enough to meet your height to width aspect ratio, whether that's 2:1 or even 3.5:1. So in those instances, you really are forced into using FTAO. This graph illustrates the racking strength of three wood-framed wall assemblies. One is braced using diagonal 2x4 lead-in bracing. Another is partially sheathed with WSP wall sheathing. And the final wall is fully sheathed and includes window openings. As you can see, the fully sheathed wall with openings was able to provide up to 88% more racking resistance when compared to the partially sheathed walls with no openings. The resilience of a structure relates to its ability to withstand and recover from a disaster. Using wood structural panels, wall sheathing to create a structural shell is a cost-effective method for adding strength and resilience to your structures. I'd like to point out that some of the design recommendations found within this guide exceeds the minimum code requirements and typical APA recommendations. Here's an option to resist uplift loads between floors of a structure and could reduce the amount of hardware needed here. Our recommendation in our high wind publication is to nail the upper and lower story sheathing to a common rim board. In most multifamily projects in my territory, I notice that this area is usually filled in with wood structural panel sheathing and requires straps to resist the uplift loads. But wood structural panels can also be used to transfer the uplift forces in addition to the shear. We have a design guide to address that on our website. So how does shear wall choices affect the architectural vision of the project? Shear walls with narrower aspect ratios will allow more openings and can also be larger. For example, if we look at this wall configuration using a segmented or perforated method, we need these wall piers to meet that 3.5:1 aspect ratio. These piers are still a 5:1 aspect ratio, so we don't get to use them. Aspect ratios impact structural designs and architectural designs. The architect wants to maximize the openings, whereas the engineer has to meet the aspect ratios to count as shear walls. But if we take that same wall and design with FTAO, we only need these areas to meet the aspect ratio. The code requires shear walls must meet a 2:1 aspect ratio and can be as narrow as 3.5:1 with an adjustment applied. The area next to the doorway is 7 foot tall and divided by the 2-foot pier width, yielding a 3.5:1 aspect ratio. To the right of the window, we use 5 feet equal to the opening height divided by the 2-foot pier width for a ratio of 2.5:1. The shear wall choices also affect your building's envelope ability to resist moisture and air intrusion, the energy efficiency, and the cladding attachment. APA has a recommendation on how to mitigate bulk water intrusion and can be summarized by these 4 steps: deflect, drain, dry, and use durable building materials. Fully sheathing with WSPs is an integral part of this solution. First, deflect the water intrusion by using gravity. Roofs are sloped, the ground is sloped away from the building, and roof overhangs can minimize the water hitting the wall. The rain that does hit the wall can be allowed to drain away using exterior cladding, and the secondary code required water-resistant barrier under the cladding. If and when water does penetrate the primary and secondary water barriers, the wood assembly must have a means to dry. Wood structural panels are considered a smart vapor retarder. The permeance of smart vapor retarders is low, then the relative humidity is low, and increases as the relative humidity increases. Therefore, the increased permeance when the wall humidity is elevated allows for greater vapor movement and faster drying of the wall. As shown in this figure, water vapor permeance of 7/16 OSB is approximately 2 perms at 50% relative humidity, but increases by a factor of 6 up to 12 perms when the humidity is increased to 85%. Finally, using durable building materials and extra care in locations that are exposed to longer-term wetting, such as where wood is in contact with concrete, completes the 4 Ds of design to prevent moisture intrusion. Did you know that wood structural panel wall sheathing can be used as a code-approved air barrier system? WSP products with a performance category of 3/8 or greater are recognized as air barrier materials by ASHRAE, the IRC, the International Energy Conservation Code, and the National Building Code of Canada. Air barriers are systems that resist airflow and pressure that completely enclose the air within a building. Wood structural panels are excellent code-approved air barrier materials, as I mentioned. They're rigid and durable, which are 2 important characteristics to consider when selecting material to be a part of a continuous air barrier system. When using WSP materials, it is incumbent on the designer and builder to choose an appropriate method for sealing openings and panel joints. The joint sealant or tape manufacturer should be contacted for information on how their product works with wood structural panel substrates. For more detailed information, APA has developed a technical topic that discusses the performance of wood structural panels when used as part of air barrier systems, and it is available to download from our website. Fully sheathed wall panels provide a solid backing for blown-in insulation systems and creates an efficient, strong wall system. Spray-in cellulose, fiberglass, and mineral wool insulation can provide high R values, which is desirable in some markets. Another extremely valuable benefit that comes with continuous wood structural panels is their ability to be used as a nail base for the attachment of siding, trim, brick ties, and many other cladding types. Continuous WSP wall sheathing is a secure, code-compliant nail base that provides an easy and effective solution for attaching all claddings. Let's review some of the advantages that plywood or OSB offer when used as a nail base. They eliminate the need for cladding installers to hit the studs. They allow for the use of shorter fasteners in that it requires that the fasteners fully penetrate the OSB or plywood by only 1/4 of an inch. They ensure that cladding materials stay in place during high wind events, and they eliminate the need for additional blocking to support ventilation and siding when ends don't fall on studs. Without OSB or plywood to act as a nail base, the siding, along with any mechanical or electrical services, as well as wide exterior trim, will need to be fastened directly to the studs or to additional blocking installed within the wall framing as shown here. When it comes to fastening recommendations when using OSB or plywood as a nail base for your siding or trim, our nail base sheathing for siding and trim attachment construction guide provides an easy method to determine the type and spacing of siding fasteners to satisfy building code requirements for cladding materials which weigh up to 3 pounds per square foot. This includes wood lap and panel siding, vinyl siding, fiber cement, wood shake and shingles, synthetic stuccos, and other popular cladding materials. Depending on the fastener type, the performance category of the wall sheathing, you will find the recommended fastener substitution schedule. Note that when using ring shank nails or wood screws, the fastener substitution schedule is 1-to-1 versus smooth or screw shank nails. This benefit was put to the test by the Insurance Institute for Business and Home Safety, and the results are clear. Siding attached directly to continuously sheathed plywood or OSB walls is able to withstand the same wind and weather conditions as siding attached directly to the framing. In fact, siding need not be attached to any framing members so long as the fasteners fully penetrate the sheathing by that minimum of 1/4 inch, and the correct fastener schedule is followed. This is also true even when siding is attached to plywood or OSB through a layer of non-structural continuous insulation up to 2 inches in thickness. As you can see, even after the roof system completely failed to a high wind force, the siding remained intact. If the weight of your cladding material exceeds 3 pounds per square foot, we have a technical topic which discusses fastening requirements for that material with weights up to 11 pounds per square foot. However, this only applies when cladding materials are attached directly to wood structural panel wall sheathing. For builders who specify the use of brick veneer, both OSB and plywood wall sheathing may also be used as a nail base to support brick ties and eliminate the need to hit studs. Without sufficient lateral resistance, however, wall systems providing support for cladding and brick veneers can fail as shown here. In this case, the structure moved significantly and was unable to support the brick veneer. Here are a few more examples of brick veneer failures. Remember that the cladding or veneer is being supported by the wall, so the wall needs to be braced such that it will not deflect or rack during high wind events or an earthquake. If the wall sheathing is able to move, so too will the material attached to it, including the brittle cladding like brick veneer. In the US, IRC Table R703.8.4 specifies fastener types, sizes, and on-center spacing of brick ties when wood structural panels are used as a nail base. The required brick tie vertical and horizontal spacing depends on wind speed and level of exposure. In Canada, it isn't quite as clearly defined, but the concepts are the same. Just be sure to check with your brick tie manufacturer for more information. Now we're going to look at the constructability using wood structural panels and the hardware needed for shear wall options. In constructing shear walls, all shear wall options utilize wood structural panels in segments or fully sheathed. They can be installed horizontally, which would require additional blocking at the panel joints, or they can be installed vertically, which minimizes blocking. It's really only a matter of preference. Hold downs are required to prevent the shear walls from overturning. There are a variety of different types of hold downs and manufacturers, but the key is that they tie the wall down to the foundation or to the wall below, engaging both the wall studs and seal plate, as shown on the left, or the studs and rim board, as shown in the 2 pictures on the right. If you do reduce the hold downs, errors like these 2 can be avoided. In the photo on the left strap is not attached to the correct jack stud as per code, and the straps do not appear to have adequate coverage by the concrete. In the photo on the right, the bolt was not installed when the concrete was poured, so the framer had to install the anchor bolt after the fact with epoxy. Errors like these cause a loss of time, may require additional inspection, and more material is needed that increases the cost of construction. The next area of concern is transferring the uplift forces from the wall above to the walls below and ultimately to the foundation. There are several ways to accomplish this using wood structural panels. We can use panels for combined shear and uplift to transfer these forces by butting the wall sheathing over the rim board or by spanning the wall sheathing past the floor cavity. We can also use straps to transfer the uplift forces in conjunction with proper connections to transfer the lateral loads. For additional design guidance, see APA's Technical Note E510 and System Report SR101. As previously discussed, FTAO has additional detailing required in the form of straps when required by the engineer around the openings and blocking on the inside of the wall. So how should the corner straps be installed? They can be located on the exterior of the wall. Note the strap above the window appears to be further up than it should be. Also, this strap is not required to be continuous. Some builders will do so as a matter of convenience with coil straps. They can also be located on the interior of the wall. If this is done, the framer would still need to provide the specified nailing of the shear panel into the blocking. However, some builders prefer to install the strap on the inside for ease of construction and to avoid conflict with the window flashing. And they don't necessarily have to be continuous. This has been frequently misunderstood, and our technical note has declared that this in the latest update as well. And if blocking is installed on the inside of an FTAO wall to transfer those compression forces, remember you're installing the corner straps to the inside of the wall. The blocking would need to be flush with the sheathing and the strapping. We published 2 cases on the advantages of using the FTAO method. The first project was Las Ventanas, looks at a modern, affordable housing complex in Long Beach, California. This case study features the use of FTAO to fully sheathe the building exterior with wood structural panels as well as glue-lams and LVLs. The FTAO method facilitated narrower piers, resulting in more flexibility with opening sizes, and it reduced embedded hardware. The re-engineering of this Santa Barbara apartment complex used I-joist compatible glue-lam beams, FTAO in place of steel shear walls, which made this project more affordable, environmentally friendly, and equitable. The money saved was transferred to community amenities. The wood structural panels are there to keep the wall square and prevent racking. The more sheathing on the walls, the greater the building's ability to resist wind and earthquake. The sheathing also provides other benefits such as uninterrupted drainage plane, an improved air barrier, a continuous nail base for cladding materials, and creates a stiffer wall favorable to brittle finishes like stucco. So what are the panel installation recommendations? The wall sheathing grade, thickness, and fastening should be called out in the plans. As a minimum, IBC requires the panels be fastened at the perimeter with 8 penny common nails and 6 inches on center and 12-inch on center in the intermediate supports. But note tighter nail spacing may be specified for shear wall applications. By understanding the big picture, it's easy to see how fully sheathed walls offer many advantages. So last, I'd like to point out our APA resources for wall bracing and shear walls. A couple of resources that you will be interested in are the book titled A Guide to the 2018 IRC Wood Wall Bracing Provision, which was co-authored by the ICC and APA and is available on the iccsafe.org website. Another resource is the publication Introduction to Wall Bracing, which can be found on our website at apawood.org. We also have a wall bracing calculator for residential structures. The calculator is updated for every code cycle beginning with the 2009 IRC and is currently updated to the 2021 IRC. The calculator is accessed through our website, which also includes a quick start guide, which is available for download at the start page, as well as a short step-by-step video on how to use the calculator. It offers the designer flexibility by allowing you to change opening sizes and braced wall segments, all while automatically checking for code compliance, and the output will match up with your drawings. As I mentioned earlier, the information gathered from our shear wall test results were used to develop design resources to facilitate FTAO shear wall design. All of these design resources are free and are available for download from our website. These include APA's technical note, designed for force transfer around openings, and APA's FTAO calculator. If you'd like more information, please visit our website. You can find the test report by searching force transfer or form M410, as well as a full hour-long FTAO webinar on our webinar page. The technical note form T555 presents the rational analysis for applying the FTAO method. This publication was developed based on APA's result from that wall 12 configuration we discussed previously. The technical note also provides a design example for an FTAO shear wall with 2 openings. As a companion to the technical note, APA also developed an Excel-based force transfer around openings calculator. This calculator is a tool for engineers to use for analyzing shear walls with up to 3 openings. The calculator's final design output includes FTAO shear wall analysis with the full design equation shown, a summary of the final design requirements, and the total calculated deflection. The analysis results fits on 3 pages and can be printed directly from Excel or saved as a PDF file to be introduced in the final calculation package. So this brings us to the conclusion of our presentation today. So we learned about the differences between braced wall panels and shear walls. We learned what the 3 methods are for designing shear walls. And we also pointed out the differences of those methods. And we referenced several APA publications that are all free to download from our website at apawood.org. So that concludes my presentation. I'll turn the mic back over to Karen to see if we've had any questions come in.
Always a lot of questions. Thank you so much, Ron. This was excellent. I am trying to go weed through the questions, answer them. We'll still be addressing those. And with the time we have left, let's get into a couple. One, and this may have already been addressed, I think it was by you, but I'm going to ask it again since it came in written a few different ways by a few different people. But what method is best suited for walls with different size openings at different elevations?
That's a good question, and we did discuss each method that has its pros and cons. FTAO does work with different size openings, although our calculator has a limitation requiring the maximum size opening be input into the software. And if you have fewer relatively small openings, the perforated method might give you the best design provided the pier widths meet the aspect ratio requirements.
Yeah, thank you, Ron. And I think you also said with the segmented, you're not even accounting for any openings. So that would be another alternative. But yes, if you're using one of the ones with openings, I think that sums it up really well. And then I know you shared a slide about the strapping, but the question is regarding strapping, does it need to be the full length of the wall? I think maybe reiterate this again, Ron.
Right. The straps only need to be long enough to allow for the full development of the tension load. The required strapping is dependent on the calculated internal tension and compression forces of that wall system. It's put in place to aid in the resistance of those tension forces through the thickness of the wall at the corner of the openings.
Yeah, and you talked about whether you do it on the outside or the inside, and a lot of that is going to be up to the engineer to decide, as well as what works best constructability-wise for the contractor. So options are available. Regard to that, so will the strapping interfere with window installation, siding, and trim fasteners? And is this a concern, or how do I address this?
The location of the straps can affect your window installation. So you can put the strapping on the inside, on the interior, but the special detailing you got to remember is required so that the blocking needs to be the full depth of the wall stud so that the strap can be installed to the blocking with the required fasteners. Also, the nailing pattern from the sheathing into the blocking should be the same nailing as what was specified by the strap manufacturer.
Okay. One more FTAO question. Can I design a wall with 4 openings using the APA FTAO calculator?
Yeah, you can use our calculator, but it is limited to 3 openings, and so typically for any additional openings, the engineer they may have their own software that can design those additional openings, or they can just do a hand count for them, and you should be good.
Perfect. looking at our time, and I see questions are still flowing in. This is great. Can I use staples to fasten shear walls?
Well, we did all our shear wall tests were used with common nails, but it may not be a fastener that's used in your market. It's our opinion that other fasteners are acceptable, provided they are equivalent to APA tested fasteners, and they're shown in SPIDWIZ and the IRC. We do have a report. Let's see, it's ESR 1539. Well, it's a code report from Isanta that has more information on those alternatives.
Yeah, very good, Ron. Yeah, because the common nails probably may not be the common fastener. So if you want to use a different fastener, just show that it's equivalent. And that is a good code report, I believe, has substitution tables for alternatives. I think I have time for one more question before we go into wrapping up. But again, I see questions are still flowing in. I'm looking at my other screen, so we will be getting to those. Anything we can't address now, you'll have a local field staff person follow up with you soon. You said shear walls can be mixed. Can I mix wall bracing types too?
Yes, you can mix. Sorry, I had to think there for a second. You can use the different shear wall methods, perforated, segmented, or FTAO, in this together in the same wall line.
Yeah, well, and again, I think the question, Ron, was what about wall bracing? So the short answer, actually, Ron's like our wall bracing person. Do you want to go ahead and answer that, or I can make an attempt on that?
No, I apologize. In wind zones design methods, you can mix some of the wall bracing panels, but in seismic, you're restricted to using the same method throughout the braced wall line, throughout the same floor. Wind's a little bit more lenient than seismic in that regard.
Yeah. All right, thank you, Ron. I think we have to wrap it up now. So again, thank you all for your questions. If we didn't get to your question, they'll be passed on to our field services team, and someone will get back to you as soon as we can. Before we conclude, a few last reminders. Make sure that you are signed up to receive our APA update newsletter so that you can be notified of our future webinars. And to do so, all you need to do from our homepage is to click on sign in the upper right-hand corner of the page, and a drop-down menu will come. You can click on that to sign up for which newsletter you like. In this instance, it would be the APA update newsletter. And then we'll look forward to sending you those updates on a regular basis. So one more reminder about our field staff. They're located throughout the country. These talented individuals like Ron are available to assist with our professional designers, our code officials, our builders throughout the country. Their individual contact information can be found on our website at apawood.org. Please take advantage of this free resource. At the end of our seminar, again, please take a moment to fill out that survey and give us some feedback so that we can continue to improve our offerings and our webinars. And with that, have a wonderful day, and thank you.